So let's start. Let me start by acknowledging the people who did the work that I'm going to present. So what I'm going to show you was done by mostly these two people here. Nesta, who is a finishing brilliant PhD student. Orko, who is a wonderful postdoc, who's going to soon move to Würzburg. And then we are helped in our understanding by these three brilliant undergraduate students who have gone on to grad school at different places in the United States, Sashwata to Cornell, Dominic to Minnesota, and Shaumadeep has just accepted an offer to Maryland. And we have benefited from discussions with HR Krishnamurthy and Manish Jain's group at IISc, Nicholas Spalding and Sayantika Bhaval at ET at Zurich, and Mandar Deshmukh at TIFR. And these are the funding agencies who support our work. Okay, let me start by reminding you very briefly about Berry phases, which most of us are already familiar with. So if you take a quantum state and evolve it in time, two phases can arise. This is the usual dynamical phase, just e to the I integral of the energy divided by h bar. And in addition to that, there is a geometric phase that can arise. So this gamma is the geometric phase. And this was what was first shown in an optics context by Pancharatnam way back in the 50s. And then subsequently, a number of people worked on different aspects of the geometric phase. And it was all put together coherently by Michael Berry in early 80s. So this today is called the Berry phase, right? And so this geometric phase within the adiabatic approximation, you can write it in such a way that it depends only on the parameter that you are changing as you move in time, okay? So this R in a crystal could be the crystal momentum K, or it could be some other parameter that you might be tuning. So using this phase, one can actually define certain mathematical objects which help in the analysis. So one can define what is called a connection or a Berry connection, which reads like this. So you take the state n, depends on the parameter r, you take the gradient of that with respect to r, and then you sandwich it with the n itself and multiply it by I. So that's the Berry connection. It turns out that this is not gauge invariant, so it's not an observable. But if you take the curl of this object, which gives us the Berry curvature, that is well defined and gauge invariant, so one can measure this. It turns out that these Pancharatnam Berry phases are in fact, they are underpinning a lot of different quantum phenomena, and one of the most celebrated ones is the quantum Hall effect. So we already had a very nice introduction to the quantum Hall effect by Professor Ajit Balram back on Monday. So what is it? Just to remind you, you just take a 2D electron gas, you apply a perpendicular magnetic field, and you measure, after applying a voltage in one direction, you measure the current in the other direction. So it turns out that you can write the conductivity sigma AB in this way, where omega is your Berry curvature that I just showed you. F0 is the Fermi function, equilibrium Fermi function. E and H are electronic charge and Planck's constant. This epsilon ABC is the Levi-Civita tensor. And you integrate this object over the crystal momentum. Turns out, quite remarkably, that this transverse conductivity is actually remarkably well quantized, 1 part in a billion and so on. So that is now actually used as a resistance standard, in fact. The key thing here is that we need to break time reversal symmetry, right? And here it's mostly done by applying an external magnetic field. You can also do it if the material has some intrinsic magnetic order, then that by itself breaks the time reversal symmetry, okay? So that's the quantum Hall effect or the linear quantum Hall effect. So as I said, this effect vanishes if you have time reversal symmetry, right? So if you don't have a magnetic field, you don't have a magnetic order, then you don't get this effect. And in this absolutely brilliant paper by Soderman and Four in 2015, it was shown that even in time reversal invariant systems, it is possible to get this kind of a Hall effect, but you need something else. You need to break inversion, and there are some other constraints that I'll come to. So this was, of course, building on some earlier work by Ornstein and Moore and others, but they called this effect a nonlinear Hall effect. So one can write down, just like I showed you the conductivity in the previous slide, one can write down the second order response within the Boltzmann framework, which looks something like this. So outside there are some prefactors, tau is the relaxation time, this again is the Levi-Civita tensor, and again inside this integral, you have something which looks familiar. So if you look back at this slide, that was the Berry curvature times the Fermi function. Now you have the derivative of the Berry curvature times the Fermi functions. So this is the derivative with respect to the crystal momentum. Okay? So this object is the key, this kernel is the key to seeing the nonlinear Hall effect or the second order Hall effect. So this object was termed by Soderman and Fu as the Berry curvature dipole. So this object here is the Berry curvature dipole. And why is it a dipole? So that can be understood by looking at plotting this kernel as a function of k in your Brillouin zone. So this is one of our previous works where we just plot this. The details are not very important, but if you look at the distribution of this object in kx and ky, clearly it has the shape of a dipole. That's hence the name Berry curvature dipole. And then one can generalize this to higher order moments. You can take second derivative, third derivative, and so on. You can get a quadrupole, octupole, etc. Okay. So turns out that the experimental demonstration was actually not very far behind. So within about 4 or 5 years, this was first experimentally seen in few layer and bilayer WTE2 by the MIT and Cornell groups in these two papers, which appeared more or less simultaneously. So they had this kind of a device geometry where they had dual gates, top and bottom gates. In between were your WTE2 layers, and then these were sandwiched between boron nitride. And then what they were able to do is scan this back gate at a given value of the top gate, and then look at the response at 2 omega. So remember, this is nonlinear response, second order response. So they measured the voltage response at 2 omega when they applied a current at a frequency omega. Okay, and then in this kind of a device geometry, they had all sorts of voltage traces that they could measure between different combination of electrodes, and turned out that these are in line with what you expect from Soderman and Fu's theory. Okay. Subsequently, there have been a number of other material systems where these effects have been measured or signatures have been found. This include the twisted double bilayer graphene. This is work from TIFR. There's also some work on corrugated graphene where these authors were able to put graphene layers on steps of some kind. And finally, very recently in 2023, there's work on LAO-STO oxide interfaces where they found beautiful nonlinear Hall effect signatures. And of course, there are many other systems. So I would like to highlight here our recent review, which summarizes many of the physical systems and processes for this nonlinear Hall effects. Okay, so what's the plan for this talk? So I'll focus on two of our recent works where we try to understand and tune these nonlinear Hall effects. The first is looking at graphene analogs, silicene, germanium, and stannine. Many of you might already be familiar with these materials, and how we can use an electric field to actually tune and enhance this Berry curvature dipole. And the second part of the talk would focus on chiral materials, so structurally chiral materials, where one can actually distinguish between the two enantiomorphs by using this Berry curvature dipole ideas. And kind of a disclaimer here is that we focus only on the intrinsic contribution here. So there can be extrinsic contributions coming from impurities, defects, and other mechanisms. But for the purposes of this talk, I'll be talking only about the intrinsic effects. Okay, so let's start with the first part. So let me just very briefly introduce these class of materials. So very soon after graphene was exfoliated, people started thinking about whether other elements in the same group can show similar low-dimensional structures. Turns out that some of these do. So for instance, silicon, germanium, and tin, they all lie below carbon in the periodic table. So people were able to show signatures of their structure, low-dimensional structure, by putting them on certain types of substrates. These are not as stable as, let's say graphene, but there are some signatures that these might be stable. So around 2009 and so on, there were theory predictions and then subsequent possible experiments where they were able to see, for instance, the honeycomb-like structure of this is for silicene, I believe. And but these are not planar; they are kind of buckled, as I'll show you in the next slides. And another interest was that because they have larger atomic masses or atomic numbers, therefore one might be able to use their larger spin orbit coupling, which in case of graphene is pretty much negligible. Right? So one of the driving ideas was also to potentially use them as topological materials because they have a larger spin orbit. And in fact, that also, the topological non-trivial nature was identified pretty early on by the group of late Professor Shucheng Zhang back in 2013. And he showed that, okay, it has a non-trivial gap. And by functionalizing the two sides of the, let's say, the thin layer, you can actually tune this gap. But however, the unambiguous measurement of the edge states, which should be present because of the non-trivial topological nature, that is still awaited as far as I know. Okay, so let's see what we were doing for these structures. So it's important to look at the symmetries of these systems before we look at the Berry curvature dipole. So it turns out that for 2 dimensions, the maximum permitted symmetry that you are allowed is just a single mirror line if you want to get any sort of Berry curvature dipole. Okay? If you have any more symmetries, then you can show exactly all the components of the Berry curvature dipole tensor will vanish. Okay? So this structure, so this is the structure. If you look from the top, it's the honeycomb structure. From the side, this is this buckling that I mentioned. So what we did was, this structure of course has many more symmetries rather than just a single mirror line. So what we did was we applied a very small uniaxial strain to get rid of this C3 symmetry and 2 reflection symmetry planes. And that is inevitably present in experiments because of your device architecture, substrate, and so on. And then to break the inversion symmetry, which is again an essential requirement to get get a second order response, we put an electric field perpendicular to the layer. Okay, so that breaks the inversion symmetry. Now, and then to model this system, we used a very simple tight binding model. We've also checked these results with more ab initio DFT type calculations, and they are more or less consistent. So the Hamiltonian that we use looks something like this. This is just your nearest neighbor hopping. This is what is called a Kane-Meili type next nearest neighbor spin orbit coupling, which just means that if the electrons hop in the anti-clockwise direction, you get one sign of this term. If they hop in the clockwise direction, you get another sign. And this works between the next nearest neighbor. So A sublattice to A sublattice, B to B. And finally, this is the term which takes into account the electric field. It gives a staggered sublattice potential. A sublattice gets a plus E value and B sublattice gets some other value. And yeah, as I said, this is a tight binding model, but we also checked with our DFT calculations that the results are consistent. Okay, so if you look at what happens to the band structure of the material as you apply an electric field, this is what happens. So if you are at low or 0 values of electric field, you have a gap in the system because of this the spin orbit Kane-Meili type spin orbit coupling term. And now if you enhance the electric field, the bands come closer together, they close the gap, and eventually the gap opens again. So this is kind of the critical point, and beyond which the system becomes a trivial 2-dimensional insulator. This system is a quantum spin Hall or a 2D topological insulator. So if you made ribbons out of this material, you get edge states running around. Okay, so this was known before. So based on this, we can put together sort of a phase diagram if you like. So here on the vertical axis, I have the band gap. On the horizontal axis is the electric field. So at low values of the field, you have a quantum spin Hall insulator. And then as you increase the field on both sides, positive or negative, the gap goes down, closes, and then opens again, the system becoming a normal or a trivial insulator. So we realized that something interesting is going on near these gap closing points. So we focus our attention near these critical values of the electric field. And one can look at what happens to the Berry curvature. I know it's not very clear on this screen, but what happens, so this is on the left side of the critical electric field, this is on the right side, so this is a non-trivial material, this is a trivial insulator. The Berry curvature has actually changed sign. If you look at this band, this is colored blue, so it has some negative value of the Berry curvature. This is red, positive value. On the other side, it's just reversed. So this is a sign of a topological phase transition, and that also indicates to us that because the Berry curvature is changing sign, interesting things could also be going on with the Berry curvature dipole. Okay, so we go ahead and actually calculate what happens to the Berry curvature dipole. So in this system, turns out that the Berry curvature dipole tensor has only the xz component to be non-zero. That can be shown. It's not too difficult to show. And so here I plot that non-zero component, dxz, as a function of the Fermi level, E minus EF, for the 3 systems, silicene, germanium, and stannine. And as you can see, there's a giant peak in the Berry curvature dipole near the Fermi level. And this is plotted for the values close to the critical electric field. And as you see for both, or for all three systems, these values are quite large, of the order of a couple of hundred. And if you compare, just to give you a feeling for what are the numbers for the TMDCs on which the experiments were done, for example, for WTE2, if you do a same calculation, you'll find that these numbers are of the order of 0.1. So these values are 2 orders or 3 orders of magnitude larger than what is present in TMDCs. Okay, and then what we can do is see what happens to the value of this BCD at the Fermi level as a function of the electric field. Okay, so this is for silicene, then germanium, and stannine. So this is what happens as you traverse this critical electric field. You actually get a change in the sign of the BCD, which looks something like this, and this happens for all the three systems. In fact, we can write down a very simple 2-band model to show that whenever there's this topological phase transition, you would see this kind of a peak dip structure occurring in the Berry curvature dipole. And so this of course, if one can measure this, then that would also serve as a signature of measuring the topological phase transition. And as I mentioned, the values that you see here are actually highest among the 2-dimensional materials, the untwisted ones. There have been recent theoretical studies on twisted WTE2 where the values are even 1 order of magnitude larger than this. But these are still larger than TMDCs where the experiments have been done. So we are hopeful that perhaps these can also be measured in future experiments. Okay, so let's switch gears and now move on to the, yeah, please, sure. Yeah. Right. Right. Yeah, you're right. So basically, the thing that spin-orbit coupling changes is that the value of the electric field that you need becomes larger and larger as you go towards tin. So if you look at the number, sorry, the plot is not very clear. So if these numbers are, let's say, 0.01 of the order of that, then here for germanium you would need, let's say, 0.1, and for tin you would need something like 0.2. So that's because you need larger and larger fields to actually close the gap and then open again. The values of D, on the other hand, are mostly set by the gap closing. That doesn't, the smaller your gap, so closer we can tune to the exact gap closing point. Ideally, it should diverge when your gap is precisely 0. It's not defined in some sense because in the denominator there's some gap factor. Okay, any other questions before yeah. Yes, around this point where it changes sign. Correct. Right. So there's as such no direct connection between the dipole and the topology, right? Because as you see on the right side, it's trivial, but still you get a dipole, right? So it's the Berry curvature itself and that integral in some kind which is related to a topological invariant, not the dipole. Yeah. It's not a signature. The sign change is a signature of the topological phase transition, but it's not the values are finite values are not a signature of topology. Okay.
Comment. Yes. So the fields here are like a megavolt per centimeter, right?
Yes.
Very huge.
Yes, absolutely.
Are they practical?
Well, yeah, that's a very, very good and important question, but I don't know. As far as I know, these are it's even difficult to actually make these freestanding layers. So this would be the next challenge in some sense. But I don't know, maybe the experimentalists can help me that whether these are reasonable fields. With pressure, yeah. 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 Right. Okay, thank you. All right, so let's switch gears and move to the next part of the talk where I'll tell you about chiral materials. Just a reminder of what is chirality. So this chirality idea was known for I guess millennia, but was first formalized by Kelvin in 1890s. where he said that if you have any geometric object, then it is chiral if you cannot superimpose it on its mirror image, right? So for example, my left and right hand, they are mirror images, modulo some imperfections, but I cannot superimpose them. If I take them like this, I cannot superimpose them, so they are chiral, okay? And of course, same idea applies to a shoe. Your left and right shoe are chiral. So you can see them, this manifestation of chirality in your real life. And of course, the ideas are also widespread across other domains like chemistry, biology, for example, the DNA structure that is chiral or helical, and other fields. So what about chiral crystals? So it can be shown using very sophisticated group theory arguments that a crystal structure will be chiral if the space group consists only what are called proper operations. So these include rotations and translations, okay? Only rotations and translations are proper operations, okay? All other sort of symmetry operations are not proper, they're called improper operations. And one of the kind of hydrogen atom of chiral systems is that of elemental tellurium, where one of the enantiomorphs has this, so if you imagine these kind of chains of tellurium, so if you imagine them going into the plane, that goes one way for one enantiomorph, goes the other way for the other enantiomorph. Okay? And as I said, so other operations like inversion or mirror plane or roto-inversion or glide, they are all improper operations, so they cannot be symmetries of a chiral crystal. So now, as you see, inversion and a lot of these, inversion is what you need to break in order to get a nonlinear Hall effect or a Berry curvature dipole. So what we asked is that, okay, what happens, can you get nonlinear Hall effects in such chiral crystals or not? Okay. And recently there have been a number of other aspects of chiral materials that have been discussed, including topology, phonons, ferroelectricity, etc. Okay, so what do we do? So first we build a very simple toy model to understand and kind of get a flavor of what things will, how Berry curvature dipole will work out. So what is that model? So it's a honeycomb model, which is sort of inspired by graphene and DNA in some sense. So it's a 2D model. So here is the schematic. So I have two sublattices, just like graphene, A and B if you like, and then all the nearest neighbor bonds, so these are these solid lines, they are unequal, unlike in graphene. So in graphene, there's only a single hopping parameter for nearest neighbor hopping. So here we make them all unequal, so we call them T0, T1, T2. And then there is a next nearest neighbor hopping, which is not like the Cain-Valley term, it's just a real hopping, where this becomes finite for one enantiomorph, and so the left-handed hopping becomes finite for the left-handed enantiomorph, and right-handed hopping becomes finite for the right-handed enantiomorph, which is what is giving you the chirality. I'll just show you the Hamiltonian in a minute. So here's the Hamiltonian. So Tij is just the nearest neighbor hopping. Now remember they are unequal, T0, T1, T2. And then there is this next nearest neighbor hopping, which takes you from A sublattice to A sublattice or B sublattice to B sublattice. That is finite. So these G's are, for example, GL will be 0 for a right-handed structure, and GR would be 0 for the left-handed one, and vice versa. Okay? And overall, this structure breaks inversion. It's also chiral. Okay, so we can go ahead and actually calculate the Berry curvature and see what happens. So it's a very simple two-band model, so we can do this analytically. So here I show you the, as a function of energy, the band structure around one of the high symmetry points, and superimposed on top is the Berry curvature. So blue means negative, red means positive, and so on. So because we have broken inversion, there is a non-zero Berry curvature. It will be opposite at the K prime point, where the signs would be interchanged. And as you would expect, these are concentrated near the band edges because that's where the denominator in the Berry curvature expression sort of vanishes. So this is for the left helical or left enantiomorph. We can do the same thing, calculate it for the right enantiomorph. And you see the band structure is of course identical. The value of the Berry curvature though is opposite. So now the conduction band has this blue color, so it's negative Berry curvature. The valence band has this red color. These are flipped between the left and right enantiomer, right? So that's the key. And now this gives us an idea that, okay, because the Berry curvature dipole is sort of a derivative of this Berry curvature. So what it's going to do is probably also going to change sign. Okay. So we go ahead and actually calculate it. So for this model, it turns out there are two non-zero components of Berry curvature dipole tensor, dxz and dyz, and we plot both of them. So the blue curves, the left panel is for the right enantiomer of the right panel. Sorry, this is dxz, this is dyz as a function of the Fermi energy. The blue is for the right enantiomer, red is for the left one, and you see the dxz component, they are exactly opposite for the right and the left one. Similarly, the dyz are also exactly opposite for the two structures. Okay, so that gives us a feeling that okay, possibly for chiral materials, you can distinguish the two enantiomorphs by using the Berry curvature dipole. So then you might ask, okay, what about real materials? This is just for a toy model. Okay, so we go ahead and actually do density functional calculations for a few different chiral systems. So one of the examples that I'm going to show you is that of this NbSi2, which is a chiral metal. So the structure looks something like this. So you have, so these blue spheres are the silicon and these green spheres are the niobium. So in one structure, you actually have these NbSi, Nb chains that are going one way. And in the other enantiomorphic structure, they go the other way, right? So those are the two chiral pairs. And if you look at the band structure, it's metallic, and both the structures have exactly the same band structure. And this is a standard GGA type calculation. There's nothing fancy here, including spinometer. And this is metallic, and predominantly the niobium d states contribute near the Fermi level. And as I said, the band structure is identical for the two. And we can go ahead and look at the Berry curvature. So again, I show you the bands along the certain high symmetry directions, and the colors tell you what is the Berry curvature sign and magnitude. Blue is again negative, red is positive. You can see there are a number of these, what we call Berry curvature hotspots, especially near these band anti-crossing points where the values of the Berry curvature are pretty large. And now you can notice, so this is the left, this is one enantiomorph, this is the other one. If you focus, let's say here, then the top band has a red color, this is blue. For the other enantiomorph, this is reversed. Okay. The Berry curvature has actually flipped sign between the two chiral structures. So before we actually look at the computation of the Berry curvature dipole, we can also look at the symmetries. So the crystal point symmetries actually impose constraints on the BCD tensor, as I had mentioned before. So you can write this equation where D is the tensor, the BCD tensor. S is the representation of the symmetry that you are looking at. So determinant of S times S ds transpose should be equal to D itself because the structure obeys certain symmetries. Okay? So now we can do this analysis very simple for NbSi2 just by enumerating all the symmetries that the structure has and writing down the matrix representations of those symmetries. And what one finds is that the D should take a form like this. So all the off-diagonal elements would vanish and only the on-diagonal ones would remain, with the constraint that the dxx and dyy would be equal and dzz would be negative of twice of the other two components. And then we can calculate this using our DFT calculations. And here I show you the BCD as a function of the Fermi level. There are three components here, the dxx and dyy overlap, so you see only two curves. This is for one of the enantiomorph, this is for the other one. Let's focus on, let's say, the red curve, which is one of the components. So you see it goes something like this. For the other enantiomorph, it's exactly opposite. So all the components, it turns out, have opposite signs for the two enantiomorphs. And the peaks are occurring. We can connect the peaks due to rapid changes in the Berry curvature. We can go back and connect it to the band structure. And if you look at the values, they are slightly smaller than the TMDCs at the Fermi level. So presumably this is also something that is measurable. Okay. So what we sort of propose is that maybe one can use this nonlinear Hall effect or second order Hall effect to actually as a transport way to distinguish between the enantiomers. As we know that there are optical ways to distinguish between them, but perhaps this could be a transport experiment that can allow distinguishing between the two. Of course, the caveat is that we are considering only the intrinsic parts, right? If there are extrinsic contributions which can mask this, then of course you will not be able to distinguish between them. But that is something we are investigating, whether the extrinsic effects keep the chirality in some sense or not. Okay, Let me quickly end by giving you one more example. So we can also do the same exercise with tellurium, which, as I said, is a favorite of people looking at chirality. So the structures are the following. You have these chains going in or in one direction or the other direction. And here is the DFT band structure. One little problem here is that if you use standard LDA or GGA, then you get a very small gap for tellurium, which is not consistent with experiments. So you have to use what are called hybrid DFT, as Shobhana mentioned in her tutorial on Monday. So you can do that, and then you can get a little bit more accurate band structure. But our results are kind of sort of agnostic to whether the gaps are large or small. And then you can go ahead and actually do similar exercise. Here I show you the bands, and the color tells you the Berry curvature values. Turns out that there is another interesting aspect of these materials, that there are while points in the spectrum, so slightly away from the Fermi level. So these are the while points. It turns out that they have a kind of a different chirality, which has nothing to do with the structural chirality. So they have this topological charge, which can be +1 or -1 or other integers. It turns out that that also switches between the two chiral structures. So one structure has a particular value of the topological charge, the other has an opposite value of the topological charge. But anyway, that's something aside. So now you can compare the components, they are opposite, and then you can go ahead and actually calculate the Berry curvature dipole components as a function of the Fermi level. Again, they're opposite in sign. Here there are slight imperfections because of certain problems with the technical issues with something called vanirization, but I can discuss more if you're interested. So with that, let me end. So in summary, what I showed you were two examples of how to tune Berry curvature dipole. One was using these graphene analogs, silicene, germanium, and stannine, where I showed you how, using an electric field, one can actually tune the gaps and therefore the Berry curvature dipole. And then the sign of the Berry curvature dipole can serve as a signature of the topological phase transition. And the second part, I showed you how possibly Berry curvature dipole can be used to distinguish between two chiral structures. Of course, here we cannot assign absolute chirality, in the sense we don't know which one is left, which one is right, but the difference between them perhaps can be gauged by doing these kind of transport experiments. And here are the references, and here's the recent review that we wrote if you're more interested. With that, let me end, and thank you for your attention.
Thank you for a very nice talk. Time for questions.
Very nice talk.
Thank you.
I want to make a question/comment on the chirality. So you showed an IBM disilicide, right? So that those are, so that's 6 sub 2 to 2 and 6 sub 4 to 2. So these two groups come in enantiomorphic pairs. So there are 22 such crystal systems, and they are called chiral groups.
Right.
But then there are 65 groups that are called Sankey groups.
Yes, yes.
So although they are not enantiomorphic, they can have chiral structures, right? So
yeah. So yeah, that's a very nice point. So I don't know what you would. So there are no pairs, right? So, but they would still show Berry curvature dipole because they break inversion, as you pointed out. But there would be no kind of comparison, sort of left and right, right? Is that right?
I mean, does your theory apply to this?
Yeah, you can do the calculation, actually get non-zero Berry curvature dipole that you would. For example, we did it for COSI, which has this cubic structure, but there is no left and right partner in some sense.
Right.
So there, by applying strain, you can actually get this Berry curvature dipole, but there is no other partner to actually compare.
So there's no flipping, and there's no other partner to do this.
Right.
Okay. So that's an interesting. Okay, so this applies only to the enantiomorphic.
Right.
Oh, thank you for the talk. Very nice talk. So again to this chiral metal. So you point out it's a diagonal very curvature dipole,
Right.
Which means it's a rectifying kind of response.
Yeah.
That might actually suggest that if you would do crystal growth and you would look for only one chirality, and you could perhaps set off the energy balance between the growth of the two chiralities by an electrical field, by a rectifying electrical field. So you might actually grow. Did anybody think about that, or
No, I did not know about that.
to distinguish between two antiomorphs and growth by electrical fields?
So what I guess what you're saying is that when you do the growth, you apply a field as you're doing the growth.
Exactly.
And then that preferentially lets you grow one or the other enantiomorph.
Yeah, because one will have, say, a lower resistivity and less dissipation than the other one, well, in second order.
I see. That's an interesting idea. Maybe I'll ask you more questions.
Any other?
Right. Yes, yes. So, yeah, I absolutely agree. So if you look at the bands, of course, there's a small gap. Turns out that most naturally grown tellurium is p-type, as you know. So if it's p-type, then your Fermi level lies somewhere here. And then you actually can do the same transport experiment.
So you essentially are depending on some systems.
Right. Pull the Fermi level down, yeah. Turns out that most cases it does happen, but of course, if you have a chiral system where it's really a semiconductor like HGS or something, then you would have to actually make some defects or gate somehow.
And also, tellurium is an interesting system. If you have, instead of bulk tellurium, if you have either other than film or one-dimensional systems,
Right. I believe it would, yeah. We have not done the actual calculation, but just from looking at that model that I showed you, right, that very simple graphene plus DNA type model, I think it should work. But that's, again, a very interesting idea. Perhaps we should try this tellurine, what people call tellurine. We should try that. I'm sure that should work.
Any other questions?
What extra information you are getting out of this nonlinear Hall effect that you cannot get from linear Hall effect?
That's a very nice question. So, for example, as I showed you, right, these are all non-magnetic materials, and I'm not including any magnetic field, right? So it can probe certain structural things. Like here, if this was magnetic, right, I don't think the linear Hall effect would be able to distinguish between one chirality and the other, right? Because it just does not have that structural information, if you like. But for instance, that is one information that we can get. Also, there are other things. For instance, in other systems where there is no magnetism, you can get this kind of rectifying behavior that Professor Van den Brink mentioned and so on. So in many materials are not time reversal symmetry broken, right? And you would like to probe their properties without breaking time reversal symmetry. So this can be useful in all those classes of materials.
Distinguish from like anomalous Hall effect,
yes, so anomalous, okay. That's a very good question. So presumably you can, because you can lock in your frequency at 2 omega and therefore you can measure a response only at 2 omega, then yes, you can distinguish between the two. But I believe if the first order signal is very, very large compared to the second order, then probably all this will be masked. But by symmetry, for time reversal symmetric systems, you will not get any first order response.
Can you please go to the BCD?
For this one?
Yeah. So the two enantiomers are not exactly.
That's very, you saw it with a very fine eye. Yeah. So that small changes are because of the vanirization. So we use standard maximally localized vanirization. So the symmetries are not exactly identical, and therefore the traces are not exactly identical. If we use something like the symmetry adapted Vanier functions, then they would be exactly identical. Thanks.
Any other questions? Sorry, I have one question about that part where you showed the topological transition. So Barry curvature dipole was peaking up around the transition point.
This one.
Yeah. So what filling are you using for calculating this?
This is all half filling.
Half filling.
Yeah.
Okay.
So charge neutrality point. We just put that.
Oh, so you are integrating like over entire body.
Exactly.
Okay. Thank you. Okay, if no other questions, then let's thank the speaker once more.
Thank you.